Hi, this is Farouk, and today we're going to be solving for the design moment strength of a concrete beam. So what we're going to actually do in this video, or this practice question, is use a flowchart I developed for us for concrete beam analysis and design. So for example, we want to find the design moment strength, right? And we know to get that final answer, there's going to be a flow of steps. And that's what the flowchart shows us. It's going to be like the sequence of steps we have to take to get that final answer, which is the design flexural strength or the design moment strength. And we will do the same thing, let's say, for a column, a concrete column. There's going to be a sequence or flow of steps you have to take to find that column capacity. Also, let's say you have a beam, a concrete beam, there's also that spacing, right? The stirrup spacing. And we know the FE handbook talks about that, and there's going to be those simple flows of steps that you have to take as well to find that spacing or the maximum permitted spacing. So just know this is what the flowchart is going to show us. We have one for concrete, and at the very end I'm going to show you one for steel as well, and these are yours. So all you have to do is put your email. I'll send it to your email and you'll get the PDF for both. All you have to do is put that email. So here, if you like this practice question, make sure to check out the other videos I have. Check those out, practice on your own, attempt this thing by yourself first, then see me go through the solution. And lastly, if you're looking for a Civil FE exam review course, I got you covered. So this course is no joke. For the Civil FE exam, we're going to break down each topic. So for each topic, we're going to do plenty of practice questions, and in fact, for the whole course, we're going to do hundreds of practice questions. And for these questions, I'm going to show you the step-by-step solution. Most importantly, I'm going to show you the process that you can use to arrive at that final answer. Also, I'm going to cover exam tips and tricks that you can apply as soon as possible to increase your speed and efficiency for something like the FE. And we will talk about calculator tips and tricks, whether you're using the TI or the Casio, doesn't matter. I cover both. So if you're looking for a Civil FE review course, please check out the link in the description below. And if you have any questions at all about the FE, about the course, or anything in general, you can always reach out to me directly. So now let's actually do this practice question. So now we know the design moment strength in kip foot for the beam section shown is most nearly what? So we're given the section and we're given the answer choices. So what I want you to do first is pause this video and attempt this on your own, struggle with it. This is the best way to learn. Make these little mistakes and struggle with this and see if you can get the same answer I get at the very end. So pause it, attempt it, and struggle with it. If you get stuck, you can watch me do that solution. So now, what I'm going to show you first is going to be the flowchart that I talked about initially. And it's going to be for concrete structures. So we know concrete structures, if we keep it simple, for something like the FE, we're going to be analyzing beams and columns. So here, we know under beams, we analyze for flexure and shear. And flexure is actually what we're going to look at. The design moment strength is the same thing as design flexural strength. So what we're going to do is go under beams, we're going to go to flexure, and we're going to go down and apply these steps. And we're going to solve for that design moment capacity. And this is what this is essentially showing us. So for shear, you have the same idea. You can find the spacing, or you can find your nominal shear capacity. And also you have the columns, same idea. You have a sequence or flow of steps you can apply. And I just want to note that for the factor design loads, I just put that there because many of us tend to forget this, but if you do a lot of these examples, you'll probably have these memorized. The factor design loads is what we always use. Although we're not using it here, make sure you know this and always use the factor design loads in your analysis. Always, analysis or design. So now what I'm going to do first is denote what we want to find. It's the design moment strength. So I'll write that down here as what we want to find. And that's going to be phi mn. That's what we're finding in units of kip foot. The units are important. We want kip foot at the end. So we know here phi mn. Phi is going to be like your safety factor or resistance factor times the nominal moment. So we always include the resistance factor when you're finding the design. Anything design, include your resistance factor. Multiply it by the nominal moment. This is what we're finding. Now, what we're given is actually the cross section, and it basically shows us everything we need in terms of dimensions, and we have the concrete properties and some steel properties. So what I want to say here first is define certain dimensions with their respective variables. That can be tricky, especially with the D. So we'll talk about that. So let's start with the simple one first. That 14 inches. 14 inches is going to be our B value of 14 inches. And that's actually defined under those definitions in the FE handbook for the design of reinforced concrete components, right? So we know B is going to be the width of the compression face of the members in inches. It's just 14 inches. We call that B. So now the next one we're going to define is this one. What's that going to be? So that is actually two things in this case. It's going to be our D, just D, which is going to equal to our DT. Okay, let's define those, what the handbook says. That one can be tricky. So D, it says distance from the extreme compression fiber to the centroid of the longitudinal tension reinforcement. So basically it's the distance from the compression fiber to the centroid of the tension reinforcement. So that's just D, right? It makes sense. And side note here, I know this is off topic. Let's say you had two layers. Where would the D be? Distance to the from the extreme to the centroid of the longitudinal tension reinforcement. So which centroid? You have to take the distance in between. So if you had two layers, the D would go like this, right? It would be to the centroid of both of them. You basically take the average of the centroid of the top layer and that bottom layer of rebar or steel. So that would be the D for that case. So just note that. That's just a note, and it can be tricky if you do not know that. So that's going to be the D. D in this case is 20 inches. So I'll write 20 inches for that one. And it's going to equal to the DT as well. DT, distance from the extreme compression fiber to the extreme tension in the steel. So it has to be the extreme tension. So we know in this case, this is the very last row. We only have one. But if the row was here, DT would actually be this, right? It would go to the centroid where you have the extreme tension where that steel is placed. So that would be DT for that case. So I just wanted to note that because it can be tricky. So now we know here that this 24, we call that the H. So that's going to be 24 inches. And basically we have it labeled. So that's what we're given. So now let's go into that solution. For the solution, we know the goal is to do what? Find that design moment strength. So what I'm going to do is use that flowchart. And okay, we know we're looking at flexure. So first this says the design moment strength must be greater than or equal to the ultimate internal moment developed. So it's gonna, the design, it makes sense. It has to be bigger than the actual moment or the service moment that's developed in the beam based on the loading conditions. So it has to be, or else it just fails, right? So we're trying to design it to be bigger than the service moment or the actual moment that's developed, which is denoted as MU. That's the actual moment developed. This is the design. So that's an important part when you're doing design. Always check that and always make sure that's true. Then we know that the equation used to find the nominal moment is denoted in the FE handbook, and this finds the nominal moment. We're going to apply this at the very end. So this is how we get that nominal moment, Mn. Then we just multiply it by phi to get the design moment, which is what we want to find. So then it says, okay, find the depth of the stress block A. This is what we'll do first. So it's a plug and chuck. So we're going to find the depth of the stress block. So A equals, I'm going to denote the equation AS times Fy. And you take that divided by 0.85 times F prime C times B. So now we know AS. What's AS? We know in the FE handbook, it's defined as the area for steel, and that will be area of the longitudinal tension reinforcement. In this case, we have 4 number 9 bars, right? 4 of them. And now I'm going to show you, I brought these actually in this note or in the PDF here, that for a number 9 bar, you can use this table. It's in the FE handbook, and the area is 1 inch squared. So we have 4 times 1. It's just 4. So for this one, it's simple because 4 times 1 is just 4. So we have 4 inches squared. And that's going to be the AS for the area of the steel. So I'll write it like that. We take 4 times 1 inch squared. Again, the 4 is for the 4 number 9 bars at that bottom, right? So then we take times Fy. So Fy is going to be actually given. That's 60 psi. But real quick, I want to save time, and we know we want kip, right? At the very end, that units of force of kips. So PSI, I know I can convert that to kip. I just divide by 1,000. There's 1,000 pounds in 1 kip. So we take that 60,000 divided by 1,000. Basically, you cancel those 3 zeros, and you get 60 KSI. So I'm going to use KSI in my solution. 60 KSI for Fy. So let me put 60 KSI. Then you take that divided by 0.85. You multiply that by F prime C. So F prime C is going to be the compressive strength of the concrete. That's 4,000 PSI. And again, I want to have that in KSI. I like using it in KSI because I want kips at the end. Let's convert it to kips. KSI, kip per square inches. So you just divide by 1,000, or you cancel the 3 zeros, and you get the 4 KSI for the concrete compressive strength. And that's what I'm going to do for this one, 4 KSI. Then you take that times the B value. The B value is 14 inches. So 14 inches. So note here, inch, kip per square inch, kip per square inch, inch. It looks good. So as an output, we should get A in terms of inches. So now when you solve for A, you get 5.042. So double check that with me and check my math, please. But you should get that in inches. So now we have the A value, and that's step 1. That's going to be the first step. Step 2, let's go to that flowchart. What does it say after that? So we know after this, we will find the beta 1 value. So the beta 1 value is on this page, and we can simply find that by actually using this table. It's in the FE handbook. So in this case, for a certain range, let's say based on the concrete compressive strength, we can get beta 1 to be this if it's equal to 2,500, and in the range of 2,500 equal to 2,500 and equal to 4,000. Note that it's less than or equal to, and this one has to be less than or equal to. So if it's equal to 4,000, it must be this one. This one's not equal to, right? This one is between that 4,000 and 8,000. It's between. It doesn't have that equal to dash at the bottom, right? And this one, when F prime C is equal to 8,000 or bigger, you use this one, use 0.65. But in our case, we know there's an equal here. It's equal to that 4,000 PSI, so it's going to be 0.85. So to find that beta 1, beta sub 1, it's 0.85. Now, let's go to the next step. We know now we want to find, after beta, we want to find the strain in the steel, in the extreme tension where the steel is located. So we can use this equation or this equation. Which one would you use in this case to save time? We found beta, we have dt, we have A, right? Or you could use this, but you have to find C first. And how would you find C? You would find C because we know there's a relationship between beta, that beta 1 value, A and C. It says A equals to beta 1 times C. So basically beta 1 is that ratio of A over C. So it looks at that stress of the Whitney stress block. It looks at how much stress there is based on that ratio of that stress block. But that's kind of beyond this calculation-based question. But just know, if you want to find the C, you would just rearrange this and solve for C. You can get C. We have beta, we have A, we found A, and you can get C and use that other equation. But the one I used is going to be this one. And let's actually use that to find the strain in the steel for the tensile reinforcement. So the strain is going to equal 0.003. We take beta 1 times dt minus the A value, and we take that divided by A. So ET is going to be 0.003. Beta 1, we said 0.85. You multiply by dt. What's our dt? We stated that initially. It's 20 inches, right? Put that 20 inches. Minus the A value. The A value is 5.042 inches. Close that, and we take all of that divided by 5.042 inches. So now we find epsilon t, the strain, and that equals to 0.00712. So we have the strain now. Next step. So what's going to be the next step? So next one is going to be a check. And I put this just in case they ask you a conceptual question. We usually always do this check, and we make an assumption what's the big assumption when you're doing this analysis? That the steel is going to fail first, or the steel yields first before the concrete fails. We always want that to happen. We always want to have a tension controlled design or analysis. It makes sense why, right? You want that steel to fail and show that indication of deflection when the steel yields at the bottom of the beam, right? And we know the cracks initiate first, then after that, what starts failing is going to be the steel, and it causes some bending. It's an indication of failure before the concrete crushes. We don't just want a sudden crushing of concrete, so we want to always ensure that the steel has yielded before the concrete crushes. So we're going to check this. So all we do is get that ET value, and it must be bigger than the actual yield strength of the steel. And the way you do that is as follows. So for number 4, it's just a check. So we will check that the steel, the strain in the steel based on this design or specific section is bigger than the yield strength, or the actual yield strain of the steel. So we know we already have ET, right? The actual strain that we calculated. We have to check if it's bigger than EY. So how would we get that EY? So I'm going to give you the basic equation. EY is going to equal to our what? We take the Fy for the steel, which is like the yield stress for the steel, and you divide by our modulus of elasticity for the steel. So here you can prove this by actually looking like at a stress strain diagram. So on the y-axis you have the stress, and the stress we will denote it as like Fy. Sometimes it's given as sigma, but in this case, no, Fy is like your yield stress. And on the x-axis, we have the strain, right? Which is like our epsilon. So if you look for steel, it looks something like that, which is what we usually assume for the concrete design. And we note here that in the linear region, we have something called that modulus of elasticity, ES. And in this case, it's for steel. So that modulus of elasticity is the slope, and the slope is the rise over the run. The rise is the y, so for the y you have Fy, which is like your y-axis, right, for the yield or the stress. And for the x, you have the epsilon y, right? And here, if you can just prove that here, we know Es, the slope, is going to equal to the rise over the run. The rise is Fy, the run is going to be Ey for the yield point. And then you just rearrange that and you should get that. And that's how you would get the equation for the yield stress for the steel. So now to find that, all we do is do that. Fy is going to be how much? Fy is actually given to be 60 ksi. Es, the modulus of elasticity for steel, is 29,000. So we put that 60 ksi over the 29,000 ksi. And if we look closely, those ksi units cancel, so we're looking good. Then you solve for the yield, and you should get a value of 0.00207. So now with that calculated, we will ask, is this the EY, is that, compared to this, is this one bigger than the EY? ET is indeed bigger than the EY, right? So we're okay. The steel yields before the concrete crushes. We always want that steel to yield. So now we know that since epsilon t is bigger than EY, we are okay. The steel should yield. So then we know the next step is, I'll call step number 5. Let's go back to that flow chart. So we know in the flow chart, all we do is get that resistance factor next, which is our phi. And we know I brought the table from the FE handbook. In this case, you have to check, is it tension controlled, compression controlled, or the transition section? No, I know that usually we want it always to be tension controlled. Always, always. So in this case, it's actually tension controlled, but you have to make sure you check this. So if it's tension controlled, the epsilon t is bigger or equal to 0.005. In this case, we found it to be 0.0071. That's bigger. So it's tension controlled, and the phi we use is 0.9. No, if it was compression controlled, you would have this phi. The transition, you would actually have to do a calculation. Anytime for shear and torsion, use 0.75. Any shear, always use this for your resistance factor. And bearing on concrete, for example, like compression, you use the 0.65. So in this case, we know it's going to be tension controlled, so the phi value should be 0.9. 0.9, and we're basically done at this point, right? All we do for step number 6, so we know in the flowchart it says you take your phi times mn, and we know that at the very beginning, the mn is going to be this equation. So the one you can use is going to be, you can use either one. I'm just going to use the one with the less work. We take as fy d minus a over 2. We have mn, and we multiply that by the resistance factor phi. That's all we do for that one. So now phi mn is going to equal to our value for, we know we took phi times mn, so I'm going to do phi times mn, right? What you do to the left side of the equal sign, you must do to the right. And we know mn is going to be as, we take that times fy, then we take d minus a over 2. So now phi mn is going to equal to our phi, which is 0.9. We take that times as. We said as is 4 times 1 inch squared, so it's just 4 inch squared. So I'll just write that. So it's going to be 4 times 1 inch squared for 4 number 9 bar. And we know fy is going to be the value that's given. In that case, it's 60 ksi. I'm going to stick with ksi. And then we take that times d. Our d value we set at the very beginning is how much? Let's go above. That's 20 inches. So d, you put 20 inches. 20 inches. You do minus the a value. That a value, let's go 5.042. We found that. 5.042 inches. And you take that divided by 2. So now phi mn, in this case, if I ask you what units should you get, it's a moment, so it's a force times distance. So it's going to be kip for the force times inches for the distance. So phi mn is going to equal, when you do that, you get 3775.46 kip inch. And note at the very beginning, what units did we want? Kip foot. So how would you get that to kip foot? We know there's 12 inches in 1 foot. You just divide by 12. So phi mn, you take that value, divide by 12, you get 314.622 kip foot. And that should equal to about 315 kip foot. That would be the closest answer for that one. So 315 kip foot. So if we go above, that one should actually be B. So it should be B for that one. So note that you can get this flowchart directly to your email. You just have to drop your email in the link in the description. I'll send it directly to you. And I just want to show you the other flowchart we have. So the other flowchart is a little bit more involved. It's a first draft. So if you see any errors, I'll fix it for you and update it to the latest one. But here we know, let's say for steel design, you still have the factor design loads. And we know for beams, we're going to analyze for big 3 things, right? You have the yielding, beam yielding, you have lateral torsion buckling, and you have shear. And here it just shows us through the sequence of simple steps you should apply when you're analyzing for yielding or even doing a design for lateral torsion buckling, LTB, or shear. And for columns, the same idea applies, right? You can use the equation in the FE handbook, or you can use the tables. Obviously, the tables is faster, so make sure you know how to do that for the steel structures. So just note, you'll get both of these to your email. So I hope you found this helpful. If you liked it, please leave a like or comment below. Thank you for practicing, and I'll see you in the next one.